Hello students. So here we are with the next set of explanations, that is laws of chemical combinations. The combination of the elements to form compounds, it is governed by these following basic laws. Very, very important laws, which will cover almost all the formations of the compounds. When elements combine to form compounds involving the chemical changes, therefore these are called laws of chemical combinations. The first one is law of conservation of mass. So this law, the law of conservation of mass, we have next law, that is law of definite proportions. Then we have law of multiple proportions. Then we have law of gaseous volumes, that is Gay-Lussac's law. And the last one is Avogadro's law. So the first one, that is a law of conservation of mass. What does this law of conservation of mass says? This law was being given by the French chemist, that is Antony Lavoisier. This law states that in all physical and chemical changes, the total mass of the reactants is equal to that of the products. Whether it is a physical change, like for example, the ice getting converted to water. When you heat ice, when you increase the temperature, it gets converted to water. It's a physical change. So how much amount of ice you have taken, you will get the same amount of water by volume, right? By mass or by mass. Volume, or you can say by mass. So this is a physical change. If you talk about a chemical change, the total mass of the reactants is equal to that of the products. Let me take a very simple example. Let me say formation of water. Yes, formation of water. Formation of water is not that easy process. You cannot just say I will combine hydrogen and I will combine oxygen and I'll get water. Please do remember, students, whenever you are writing any reaction, the reaction has to be chemically balanced. The number of reactants molecules should be equal to the number of products. That is nothing but law of conservation of mass. So there are 2 atoms of hydrogen, 2 atoms of oxygen. There are 2 atoms of oxygen and there is only 1 atom of oxygen. So I will balance it by writing, either I'll write half O2 here, it becomes H2O, right? So how many atoms of hydrogen? Yes. So atoms of hydrogen, if I say by number of atoms, yes. So here there are 2 atoms of hydrogen, 2 atoms of oxygen divided by 2. So there is 1 atom of oxygen. Here there are 2 atoms of hydrogen and 1 atom of oxygen. So 2 plus 1 becomes 3, 2 plus 1 becomes 3. So this is in case of atoms. If I want to speak the same in case of mass, because it is conservation of mass, right? So if I want to speak in case of mass, how do I say it? So I can take the example. Let me say I have example for formation of water. So H2 plus half O2. This occurs in presence of platinum catalyst, small amount of platinum to give H2O. So by mass, if I'm speaking, the mass of hydrogen molecule is 2 plus half. Oxygen mass is 16. 16 into 2 is 32. Yes, so it becomes 2 plus 3, 2 ones are 2 16s are. So 2 plus 16 becomes 18 grams of mass of reactants. So this side it is reactants, correct? Okay, coming this side, H2O, 2 atoms of hydrogen, mass of 1 atom of hydrogen is 1 into 2 plus it is 16. So 2 plus 16 is again 18 grams. So here also I have got product mass equal to 18 grams, which is the same. So what does this means? How much amount of reactant you have taken, the same amount of product we are going to get. So the total mass of the reactants and products is going to be the same. So the law says, the law of conservation of mass says the physical and chemical changes, the total mass of the reactants is equal to that of the products. In other way, if you want to say the same law, how can we say that? The matter can neither be created nor be destroyed. Matter can neither be created nor be destroyed. Coming to the next one, the law of definite proportions. Law of definite proportions or definite composition also we can say. This law was being given by Joseph Proust. It was being given by Joseph Proust. Now, what does this law says? What does this law says? This law says that a pure chemical compound always consists of same elements combined together in a fixed proportion by weight. If you have a pure chemical compound, it always consists of same number of elements, same elements combined together, the same elements combined together in a fixed proportion by weight, in a fixed proportion by weight. For example, yes, let us consider the example, or you can define it in another way, like a given compound always contains exactly same proportion of elements by weight. A given compound always contains exactly same proportion of elements by weight. Yes, for example, yes, let me say I'm speaking about carbon dioxide, CO2. Yes, so carbon dioxide contains by weight, okay, carbon, how many grams? There are 12 grams of carbon and 32 grams of oxygen. How 32? Oxygen has got 16, so 16 into 2 is 32 grams of oxygen. Yes, so what is the ratio? If I say ratio, 12 is to 32. So 6 ones are 6, 6 twos are 12, 6 threes are 18, 6 twos are 12. 32 doesn't go with the 6. So 2 6 are 12, 2 16s are, 2 3s are 6, 2 8s are 16. So this is the ratio. 3:8 is the ratio of mass of carbon and oxygen in carbon dioxide, irrespective of the source. Wherever it is obtained, wherever you get carbon dioxide, the ratio by mass, we say ratio by mass, it is always 3:8. It is always 3:8. Another example, we have one more example like cupric carbonate. Cupric carbonate. Yes, if you see cupric carbonate, let me say I have taken natural sample of cupric carbonate, natural sample. Cupric carbonate means it contains copper, carbon, and oxygen. If you look the percentage of copper in cupric carbonate, CuCO3, the percentage is 51 of carbon is 51.35 by mass. Yes, carbon is 9.74 and oxygen is 38.91. If I prepare same cupric carbonate in the lab, let me say it as synthetic sample, preparing in the lab. So the same sample, if you look at when I prepare cupric carbonate, the percentage of copper will be 51.35, carbon will be 9.74, and oxygen will be 38.91. So irrespective of the source, the pure chemical compound always contains same elements combined together in the fixed proportion by weight or by mass. Mass, this is weight composition, okay? It remains the same. So this is about law of definite proportion or law of definite combinations, you can call it. Next one is law of multiple proportions. This law was being given by John Dalton. It was being given by John Dalton, the famous scientist. What this law says is, if two elements combine to form two or more compounds, the weight of one element which combines with the fixed weight of the other in these compounds bears a simple whole number ratio. Bears a simple whole number ratio. Like let me say, and I have an example, H2O and H2O2. So these are the two compounds which are obtained from hydrogen and oxygen. Yes, so H2O and H2O2, where H2O here, if you see, hydrogen combines with oxygen to form H2O. So here for balancing, I'll write half. Hydrogen combines with oxygen to form H2O2. So here the one element mass is fixed. The mass of one element is fixed, correct? Which is that element with fixed mass? It is hydrogen. So the mass of hydrogen, here also it is 2 grams, here also it is 2 grams. So this is fixed. This is fixed. This is fixed. So what they say? The weight of the one of the elements which combines with fixed weight of the other. So this is the fixed weight. So this is combining with other element where the weight is varying. So what is the weight here? Here it is 16 grams of oxygen. Yes, and here it is 32 grams of oxygen. So I can say here 16 grams of oxygen combines with combines with 2 grams of hydrogen, 2 grams of hydrogen to form water. Okay. And here I say 32 grams of oxygen combines with 2 grams of hydrogen to form H2O2, that is hydrogen peroxide. So this is fixed. So I'll not consider this. The another one, the weight of one of the elements which combines with fixed weight. So this, so I can write here as weight of oxygen. Weight, rather than saying weight of oxygen, let me take as a weight ratio. Yes. So weight ratio of oxygen in two compounds. In two compounds. So what will be the weight ratio? That is H2 and H2O2. 16 is to 32. How much it is? It is 1 is to 2. So is it not a simple whole number ratio? So is it not a simple whole number ratio? If you look here, is it not a simple whole number ratio? Yes. So this is nothing but law of multiple proportions. It will be in a simple whole number ratio. I can take one more example. Yes. One more example is nitrogen and hydrogen combine to form NH3 and N2H4. These are the two compounds formed. N2H4. Let us see. So nitrogen N2 combines with hydrogen to form NH3. So it is 3 here. I'll write 3 here and I will write 2 here. Correct? Balanced. Nitrogen and hydrogen combine to form N2H4. So it is 4 here. So I'll write 2 here. So which is fixed here? The fixed one is nitrogen. So nitrogen is fixed here. But varying one is hydrogen. So I can say here, in this case, I can say, what is the nitrogen? 14, 28 grams. Here also it is 28 grams. Hydrogen 2, 3 2s are 6 and 2, 2 2s are 4. So I can say 6 grams of hydrogen combines with 28 grams of nitrogen to form ammonia, that is NH3. Yes, here what I can say, 4 grams of hydrogen combines with 28 grams of nitrogen to form N2H4, nitrogen hydride, N2H4. So this is varying. So if you want to calculate the weight ratio of nitrogen in NH3 and N2H4. So what will be the weight ratio? It is 6 is to 4. So a simple whole number ratio, 2 3s are 6, 2 2s are 4. So is it not a simple whole number ratio when you look at this? So it is a simple whole number ratio. Even you can work with the same example like a formation of carbon dioxide and carbon monoxide. For carbon dioxide and carbon monoxide using carbon and oxygen. So this law, multiple proportions given by Dalton, it says if two elements combine to form two or more products, the weight of one of the elements which combines with the fixed weight of the other, or in these compounds, it is the simple whole number ratio by weight. Coming to the next law, that is Gay-Lussac's law. So what does Gay-Lussac's law says? Gay-Lussac's law states that under similar conditions of temperature and pressure, whenever gases combine, they do so in volumes which bear simple whole number ratio with each other and also with the gaseous products. Yes, or you can say when gases combine or are produced in a chemical reaction, they do so in a simple whole number ratio. For example, combination between, let me say, hydrogen and chlorine. H2 gas combines with a Cl2 gas to form HCl gas. Yes. So how much volume of hydrogen gas? So here I have taken 1 volume and 1 volume of chlorine gas. I'm getting how many volumes? I'm getting 2 volumes of HCl. So what is the ratio? It is 1 is to 1 is to 2. So the ratio is a simple whole number ratio. So this is Gay-Lussac's law of gaseous volumes. Yes, Gay-Lussac's law of gaseous volumes. Or you can take one more example. Nitrogen gas combines with hydrogen gas to give ammonia, NH3 gas. So balancing 2 and 3 here. So here how many volumes? I've taken one volume. Here there are 3 volumes and here I'm getting 2 volumes. So what is the ratio? The ratio is 1:3:2. So it is the simple whole number ratio. This means what? One volume of nitrogen gas reacts with 3 volumes of hydrogen gas to give 2 volumes of ammonia. That is 100 ml of nitrogen gas will react with, I can say it like this also. 100 ml of nitrogen gas reacts with 300 ml of hydrogen gas to give 200 ml of ammonia. Yes, if all the gases are measured at same temperature and pressure. Same temperature and pressure. Take one more example, formation of water. H2 gas plus O2 gas gives H2O. Yes, I can balance it by writing like this. I can say 2 volumes of hydrogen gas combines with 1 volume of, so I cannot write here half. So it is a simple whole number ratio. Gives me 1 volume of water. So 2:1:1. So if I am taking 2 liters of hydrogen gas, here I'll take 1 liter of oxygen and I'll get 1 volume, 1 liter of water. Yes. So this is what Gay-Lussac's law of gaseous volumes. Gay-Lussac's law of gaseous volumes. The next one is Avogadro's law. So what does Avogadro's law says? It was given by Avogadro. Equal volumes of gases at same temperature and pressure should contain equal number of molecules. So what does this mean? Yeah, example. If we consider the reaction of hydrogen and oxygen, let me give it in a different manner to make you all understand. Let me say I have, in this block, I have hydrogen. In this block, I have oxygen. Or as the reaction, I will write. Fine. Okay, so let me take it like this. So hydrogen combining to form water. Just now I have seen 2 volumes of hydrogen combined with 1 volume of oxygen to produce water. So 2 volumes of hydrogen. So this is H2, this is H2. So H2, H2 molecules I'm representing like this. Okay, H2 molecules. They combine with 1 volume of oxygen. So this is 1 volume of hydrogen plus 1 volume of hydrogen plus 1 volume of oxygen. Oxygen molecule. Yes. And it is giving me what? Sorry. Okay, so it is giving me what? It is giving me water. So water. So we get water like this, H2O. Can I write it like this? So how many volumes of H2O I get? I get 1 volume of H2O according to the reaction. So I get 1 volume of H2O. That is water vapor, I can say. Yeah. So 2 volumes of hydrogen react with 1 volume of oxygen to give me 1 volume of water. So what does this law says? Says that equal volumes of gases at same temperature and pressure contain equal number of molecules. If I say 1 volume of hydrogen, it will have same number of molecules. 1 volume of oxygen, it will have same number of molecules. And what is that number equal to? What is that number equal to? It was being given by Avogadro. Therefore, that number is called Avogadro's number. What it is called? It is called Avogadro's number. Avogadro number. Yes, so it is called Avogadro's number. So I will mention here, yes, 1 volume of H2, it will have same number of molecules, and that same number of molecules is 6.022 into 10 raised to 23 molecules. Molecules, not moles, molecules. Another, if I say 1 volume of oxygen, it will have 6.022 into 10 raised to 23 molecules of oxygen. If I say 1 volume of water, it will have 6.022 into 10 raised to 23 molecules of water. So equal at same temperature and pressure, equal volumes of any gases will contain equal number of molecules. Will contain equal number of molecules. So this is nothing but Avogadro's law. This is nothing but Avogadro's law. Yeah. So these are the 5 laws of chemical combinations. Then moving to the very important theory, that is Dalton's atomic theory. So Avogadro's law, if you see, so this Avogadro, he made distinction between atoms and molecules. He made distinction between atoms and molecules. So note that each, if you took, as I showed the example, each of them, they contain 1 volume of hydrogen, same number of molecules. 1 volume of oxygen, same number of molecules. 2 volumes of water, 1 volume of water, same number of molecules. So equal volumes of any gases will contain equal number of molecules. So this was being proposed by Avogadro. Then moving to the next one, that is Dalton's atomic theory. See, matter, we got to know that matter consists of a small individual indivisible particles called atoms. Yes, how the word atom came, the structure of atom we'll be discussing once again all these things. How the word atom came, it came from the Greek, from the word atomia. Yes, meaning what? Meaning indivisible. So my atom was considered to be indivisible. That means that was the smallest particle which was being discovered. Greek philosopher, that is Dalton. So what he did in the year 1808, Dalton, he published a new system of chemical philosophy, and he proposed certain points on it. Yes, he proposed certain points. And what are those points? Postulates, he formulated them as postulates. They are: matter consists of indivisible atoms. That means atoms are further indivisible, cannot be divided further. Second point, all the atoms of a given element have identical properties. Example, if suppose if I take iron element, and here I take a piece of gold. Yes, so let me say this is iron and this is gold. I hope you know the symbols. So iron will contain iron atoms and gold will contain gold atoms. Take out an iron atom, compare it with another iron atom. They will be identical, both in physical as well as chemical aspects. They will be identical. Take out gold atoms, compare each of them. They will be also identical in physical as well as chemical basis. So all the atoms of a given element have identical properties. If you have atoms of different elements, now what I'll do, I'll take gold atom and iron atom. Will they be same? No. They will differ both in physical as well as chemical properties. So this is the second law. What does the third point says? So first point, matter consists of indivisible particles called atoms. All the atoms of given elements have identical properties, including identical mass. Atoms of different elements differ in the masses or properties also. Compounds are formed when atoms of different elements combine in a fixed ratio. We have seen law of definite proportions. Only when the atoms of different elements combine. So let me say H2 plus O2 gives H2O. It is not molecules which are combining. Here there are 2 atoms of hydrogen. There are 2 atoms of oxygen. So here only 1 atom of oxygen comes into consideration. So what happens? This 2 atoms of hydrogen combine with the atom of oxygen to form a compound, that is water. To form a compound, that is water. So they combine in a fixed ratio. Chemical reactions involving reorganization of atoms, these are neither created nor destroyed in a chemical reaction. The number of atoms remains the same. Therefore, we say Atoms can neither be created nor be destroyed. So Dalton's theory could explain the laws of chemical combinations. However, it could not explain the laws of gaseous volumes. Yes, there was this what you say limitation. It could explain all the laws of chemical combinations, but when we come to the point of laws of combining volumes, it was unable to explain. It was unable to explain. Yes, so this is about Dalton's atomic theory, which was being proposed in the year 1808. In some books it is given 1803. You can consider the NCERT, it is 1808. Yes, Dalton's atomic theory. Then next important aspects. Yes, atomic and molecular masses. So what do we mean by atomic mass? What do we mean by the molecular mass? All the things now we are going to discuss one by one. Hope till the things what we have discussed so far are all clear. So atomic mass, the atomic mass of an element is the number of times an atom of that element is heavier than the atom of carbon. Excuse me. Excuse me, taken as 12. Yes, taken as 12. So I'll explain it in a better way. That is the definition of atomic mass, however, but how to get understood with this atomic mass. So when we speak about atomic mass, is it just the mass of atom? No. So atomic mass, or sometimes said as atomic weight, is nothing but mass of one atom of that element, mass of one atom of that element divided by 1/12th mass of 1/12th mass of atom of C12 isotope of carbon. C12 isotope. C12 because carbon 12 is present in large abundance. So this is atomic mass. This is the definition for atomic mass. This is how we define atomic mass. So atomic mass is mass of one atom of an element divided by 1/12th mass of an atom of C12 isotope of carbon. Yes, so atomic mass. Then coming to the second one, that is molecular mass. Yes, molecular mass. So this atomic and molecular mass, they are being, how do you write the atomic or molecular mass? They are being written, the unit for that is, it is AMU, atomic mass unit. Atomic mass unit. Earlier we used to use this atomic mass unit, AMU. So suppose atomic mass of carbon 12 AMU. Yes, now it is being replaced by unified mass, unified unit, that is U. So we write it as 12U. Molecular mass. What is molecular mass? It is nothing but weight of one molecule, mass of one molecule divided by 1/12th mass of atom of C12 isotope. 1/12th mass of atom of C12 isotope. So this is the definition for molecular mass. This is the definition for molecular mass. So these two are the definitions for atomic mass and molecular mass. If you want, suppose instead of giving mass, if they have given you vapor density, then how do you determine molecular mass or molecular weight? I write it as like this. Molecular weight is always equal to 2 into vapor density of that given element, given molecule. 2 into vapor density of that given molecule. Yes, so this is molecular weight and atomic weight. Okay. So average atomic mass. If the element is particularly existing in a large number of isotopes, that time we come across average atomic mass. Suppose there is chlorine with two isotopes, 17Cl35 and 17Cl33. So in that case, what we do is we take the atomic masses of both the isotopes, add them and divide by 2. So it will be average atomic mass. So what do we mean by average atomic mass? So atomic mass of an element must be its average atomic mass, and it may be defined as average relative mass of an atom compared to the mass of carbon atoms taken as 12. Yes. Molecular mass. Molecular mass is the sum of the, or you can define it like this also. Suppose they give you a compound and they ask you the molecular mass. So how do you find the molecular mass? Let me say molecular mass of methane. So it is what? It is the masses of the elements present in the molecule. Multiplying the atomic mass of each element by the number of atoms. For example, atomic mass of carbon is what? 12. Into how many atoms of carbon? 1. Plus atomic mass of hydrogen is 1. Into how many atoms of hydrogen? 4. So 12 plus 4 is how much? It is 16 U, unified mass. Another example, H2O. Atomic mass of hydrogen is 1. Into there are 2 atoms of hydrogen. Atomic mass of oxygen is 16 into 1 atom of oxygen. So 2 plus 16 is 18 U. So this is molecular mass. Another example, atomic C6H12O6. What is the molecular mass? Atomic mass of carbon is 12 into 6 carbon atoms. Hydrogen is 1 into 12 hydrogens. Oxygen is 16 into 6. So 6. So it is 72 plus 12 plus 96. So how much you get? 180 U. So this is how we calculate the molecular masses. Yes, so molecular mass is the sum of the atomic masses of the elements present in a molecule. Formula mass is same as molecular mass. It comes for ionic compounds. Methane is not an ionic compound. It is a covalent compound. So formula mass comes when you have ionic compounds. So here, how to calculate a formula mass? NaCl. So they have given you NaCl. What is the atomic mass of NaCl? The Na, sodium is 23 into 1 atom of sodium plus chlorine is 35.5 into 1. Chlorine. Yes. So what do we get? We get 23 plus 35.5. So how much? It is 58.5. This is formula mass. Even for HCl, 1 atom of 1 is the atomic mass into 1 plus 35.5 into 1. So it is 1 plus 35.5, that is equal to 36.5 U. Yes, U. So when they ask atomic mass or molecular mass, we use the unit U. There is one more thing, or formula mass, we use the unit U. There is one more thing, that is gram atomic mass, gram molecular mass. When the term gram comes, so remember here, okay, so atomic mass, when they say atomic mass, you'll write the answer and mention the unit U. Molecular mass, sometimes abbreviated as molar mass also, write the answer and say U. Gram atomic mass, you'll write the answer and say grams. Or gram molecular mass. So you have to be very careful what is being asked. You'll write the answer and say grams. For example, atomic mass of hydrogen, 1 U. Gram atomic mass of hydrogen, 1 gram. Atomic mass of water, 18 U. Molecular mass of hydrogen, water. Molecular mass of hydrogen, 18 U. Gram molecular mass of hydrogen, 18 grams. So this should be very carefully known. Yes. So if it is atomic mass, it is U is the unit used. If it is molecular mass, gram atomic mass, we use grams. Coming to the next concept, that is mole concept. So what do we mean by a mole? Yeah, what do we mean by a mole? So mole is a unit which represents Avogadro number of particles. Yes, mole is what? It is found that 1 gram of any atom of any element contains same number of atoms, or 1 gram molecular. So rather than making it so difficult, so what is mole? Yes. What is mole? Mole is amount of substance which contains Avogadro number of particles. Amount of substance which contains Avogadro number of particles, that is 6.022 into 10 raised to 23 Avogadro number of particles. So it is amount of the substance which contains, like how you say dozen, 1 dozen of pens, 12 pens, 1 dozen of books, 12 books, 1 dozen of fruits, 12 fruits. That number is same, right? Similarly, 1 mole of anything, 1 mole of anything is equal to 6.023 or 22 into 10 raised to 23 entities. I say entities, anything it might be. So if I say 1 mole of hydrogen atoms, so it will have how much? 6.022 into 10 raised to 23 hydrogen atoms. If I say 1 mole of hydrogen molecules, see, it will have 6.022 into 10 raised to 23 hydrogen molecules. Understanding? So 1 mole of anything will be equal to this number, this entity, and that is Avogadro's number, which is abbreviated as Na. Now see, if I say 1 dozen of pens, how many pens? It is 12. Or I say 1 dozen of watermelons. How many watermelons? 12. The number is same, but will the mass be same? No, the mass differs. Mass of pen is calculated, and that will be the mass of pen. Mass of watermelon is that will be mass of watermelon. Similarly, if I say 1 mole of hydrogen atoms, it will have same number, but what will be the mass? Its mass is always the atomic mass if it is an atom. Yes, if I say 1 mole of hydrogen molecules, the number of molecules will be same, but what is the mass? It will be molecular mass. Molecular mass. Example, 1 mole of hydrogen atoms is 6.023 into 10 to 23 hydrogen atoms, and its atomic mass is 2U. 1 mole of, sorry, I'm very sorry, hydrogen atom it is, so its atomic mass is 1U. 1 mole of hydrogen molecules is 6.023 into 10 to 23 hydrogen molecules. It will be 2U, molecular mass. Understanding? One more example. 1 mole of hydrogen atoms. 1 mole of carbon atoms. 1 mole of oxygen atoms. 1 mole of hydrogen, when I write H2, it is molecules, or 1 mole of oxygen molecules, 1 mole of nitrogen atoms, 1 mole of nitrogen molecules, right? So 1 mole of hydrogen atoms, 6.022 into 10 raised to 23 hydrogen atoms, correct? Carbon atoms, same number, carbon atoms, right? Oxygen, same number, oxygen atoms. Hydrogen molecules, same number, hydrogen molecules. Oxygen molecules, same number, O2 molecules. Nitrogen atoms, same number, nitrogen atoms. Nitrogen molecules, same number, nitrogen molecules. What about the mass? This will be 1 unit. Carbon, 12 unified mass. Oxygen, 16 unified mass. Hydrogen molecule, 2 unified mass. Oxygen molecule, O2, so 16 into 2, 32 unified mass. Nitrogen atom, 14 unified mass. Nitrogen molecule, 28 unified mass. Similarly, 1 mole of water, it will have 6.022 into 10 raised to 23 H2O molecules, and its mass will be equal to 18 grams. Sorry, 18 U. Understanding? So this is nothing but mole concept. This is nothing but mole concept. Now I can club this everything. So 1 mole is equal to what all things? I can make you all understand. Yes. Example. Yes. Please try to understand this. So let me say this is 1 mole. So when I say 1 mole, see, it is equal to what all things? You'll be very astonished to look at the things here. Yeah. So 1 mole is nothing but 6.022 into 10 raised to 23 atoms, or 6.022 into 10 raised to 23 molecules, or gram atomic mass, or gram molecular mass, right? Or gram molar volume. You take volume, you take 1 mole of any gas, 1 mole of hydrogen gas, it will have 22.4 liters of hydrogen, 22.7 liters of hydrogen gas. 1 mole of chlorine gas, it will have 22.7 liters of chlorine. That is nothing but gram molar volume. Yes, even apart from this, so this is, I hope this is clear. Apart from this, I can even say, so 1 mole is nothing but 1 gram mole of compound. Compound means, so mole is equal to mass of compound divided by gram molecular mass. Yes. Then if you have an atom, 1 mole is nothing but 1 gram atom of an element. That is, mole is equal to mass of element divided by gram atomic mass, or it is equal to so many things can be understood here. 22.4 liters at STP, standard temperature and pressure. Therefore, I can say 1 mole is equal to volume in liters divided by 22.4. Yes, even it is equal to Avogadro number of particles. So I can even write it as mole is equal to number of particles. Please do remember these formulae, divided by Avogadro number. Please do remember all these formulae. Number of particles divided by Avogadro number. So if suppose they give you some mole and they ask you to calculate, it is nothing but this. This is all about mole concept. As soon as we finish with mole concept, we come across equivalent weight, equivalent mass, or equivalent weight. Yes, equivalent weight can be defined in different ways. If you are defining equivalent weight of elements, the definition would be molecular mass divided by basicity. Equivalent mass, if you are defining molecule of an element, it will be molecular mass divided by basicity. It differs. If you are defining equivalent, equivalent not element, here it is equivalent weight of acid. Yes, molecular mass divided by basicity of acid. Equivalent weight of base, molecular mass divided by acidity of base. if you are defining equivalent weight or mass of element, it will be atomic mass of the element divided by valency. Yes, even equivalent mass for salts we have, oxidizing agents, reducing agents, so many things we have. So that is all about equivalent weight. Yes, so we have discussed here so far regarding equivalent weight of acid, of base, of elements. Then we have stoichiometry and stoichiometric calculations. Stoichiometry is derived from the two Greek words, stoichion meaning element, metron meaning measure. Element measure, it differs. Are you measuring in terms of atoms? Are you measuring in terms of masses? In terms of atomic masses or in terms of molecular masses? It differs, right? Yes, example here. CH4 plus 2O2, combustion of methane it is. CO2 plus 2H2O. Yes. So coefficients, coefficient here for methane is 1, for oxygen is 2, carbon dioxide produced is 1 molecule and the water produced are 2. Yes, coefficients there. Yes. Now see, according to the above chemical reaction, methane and dioxygen are called reactants, carbon dioxide and water are called products. G indicates what? It is in gaseous forms. All the reactants and products are in gaseous forms. The coefficient 2 for oxygen and H2O are called stoichiometric coefficients. So according to the above chemical reaction, I can say 1 mole of methane, there is one, right? 1 mole of methane reacts with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water. This is one way in terms of moles. If I want to speak in terms of molecules, I can say 1 molecule of methane combines with 2 molecules of oxygen to give me 1 molecule of carbon dioxide and 2 molecules of water. Yes, this is in terms of molecules. If I want to speak in terms of liters, 22.4 liters of methane, because it is 1 into 22.4. Oxygen, 22.4 into 2, it comes out to 44.8 liters of oxygen to give 22.4 liters of carbon dioxide, again 22.4 into 2, 44.8 liters of oxygen, water. Yes, this is in terms of volume. If I want to speak in terms of grams, that is mass, CH4, 12 plus 4 is 18, carbon 12, hydrogen 4, so 12 plus 4 is 16. So 16 grams of methane, oxygen 2 into 32, that is 32 into 2, 64 grams of oxygen to give 44 grams of carbon dioxide and 18 into 2, that is 36 grams of water. So what are these? Mole can be converted to molecule, molecule can be converted to volume, volume can be taken in the form of mass. Yes or no? So these data is what it is interconvertible. It is what? Interconvertible. That is nothing but stoichiometric ratio. What it is? The calculations based on the knowledge of chemical equations. Yes, they are called stoichiometric calculations. What they are called? Stoichiometric calculations. Yeah. So if you want to find the stoichiometric calculations, first, whenever the reaction is given, you should write the balanced reaction for it. You should write the balanced reaction. Then write the molar relationships for the equation between given and required species. Then convert the moles into desired parameters. Like you can convert it to mass, you can convert it to volume. Then apply the unitary method to calculate it. Yes, to calculate it. Okay, then limiting reagent. So what do we mean by limiting reagent? Sometimes in a chemical reaction, the reactants present are not the same amount as required according to the balanced equation. So the amount of products formed thus depends upon the reactant which has completely reacted. This reactant which has reacted completely is called limiting reagent. Or you can say the concentration of the reactant which gets consumed and limits the amount of product formed is called limiting reagent. So the moles of the products are always determined by starting moles of the limiting reagents. Okay. Then we have expressions of strength or concentrations of the solutions. First one, mass percent or weight percent, W by W percent. How do we calculate the mass percent? Mass percent is nothing but mass of the solute into divided by mass of the solution into 100. So this is mass percent of a solution. Yes. Then these are different ways of expressing the concentrations. Mole fraction. How do you define mole fraction? Mole fraction is defined as the ratio of number of moles of particular component to total number of moles of solution. Let me say I have a binary solution. Binary solution contains two components only. So the component A, let me say I have two components A and B. There are n A molecules of A and NB molecules, number Na. So what is the mole fraction? Mole fraction of A. It is Na, ratio of number of moles of that component, divided by Na plus Nb, total number. So what is the mole fraction of B? It is number of moles of B divided by total number of moles of the solution. Always remember, mole fraction is denoted by sign this. So I can write here XA, I can write here XB. XA plus XB is always equal to 1. So if you are finding a mole fraction of A, you can find mole fraction of B is equal to 1 minus mole fraction of A also. It is always unity, and it is a unitless quantity. Unitless quantity. It does not have any units. So this is about mole fraction. This is about mole fraction. Okay. Then next what we have is molarity. So what is molarity? It is defined as number of moles of solute in 1 liter of solution. So number of moles denoted as capital M, number of moles of solute in 1 liter of solution. Yes. Then molality. What is molality? Small m. Number of moles of solute in 1 kg of solvent. Number of moles of solute in 1 kg. So here it is solution in liters. Here it is solvent in kg. Yes, that is molality. We have one more, parts per million. So what is parts per million? It is ppm. Parts per million is equal to parts of the component per million parts of the solution. So part of a component divided by total into 10 raised to 6 million parts, where W is weight of solute, this is weight of solvent solution, and this is 10 raised to 6 into 10 raised to 6, that is million parts per million. Yes, I can show you these things with a few examples also. Like for example, let me say a solution is prepared by adding 2 grams of a substance A to 18 grams of water. 18 grams of water. So calculate the mass percent. How do you calculate mass percent? Mass percent of A is equal to mass of a component, that is 2 grams, divided by total mass 18. Total mass is not 18, it is water. It is 2 plus 18 of A and water, right? Into 100 percentage. So 2 divided by 20, it is how much? It is 10%. This is how we calculate mass percent. Another example, calculate the molarity of NaOH solution prepared by dissolving 4 grams of NaOH in enough water to form 250 ml of solution. So it is forming, total solution is 250 ml. So what is molarity? Symbol is M. Number of moles of solute. See, number of moles of solute. They have not given us moles of solute. They have given us mass. So if they have given us mass, how to calculate moles? Formula we already know. Moles is equal to mass of substance divided by molecular mass. So what is mass of NaOH given? 4 divided by molecular mass of NaOH. Na is 23, oxygen is 16 plus 1. 24 plus 16 is 40. So 4 by 40 is how much? 0.1. So I can write 0.1 divided by 250 ml. 250 ml. So 250 ml can be written as 0.250 liters, because volume should be in liters. So what do I get? I get 0.1 divided by 0.0. So 1 by 250, It is nothing but 100 by 250 is nothing but 0.4 moles per liter. So this is how we calculate molarity. Molarity, please remember, it depends upon the temperature because volume is temperature dependent. Yes. Another question. Calculate the molality. Density, let me say density of 3 molar solution. Molar is given and its density of NaCl is given. Its density is 1.25 grams per liter, milliliter. Calculate the molarity. So molarity is 3. Mass of NaCl. Mass of NaCl in 1 liter of solution. So NaCl 3 moles are there into NaCl is 58.5. The answer comes out to be 175.5. I'm just taking an example, simple example. So mass of 1 liter of solution. 1 liter of solution is 1000 into 1.25, right? So it is 1250 grams. Since density is 1.25, so density should be converted, right, to grams. So calculate molality. So molality is 3 moles, number of moles of solute divided by 1000 mass of water solution I want, right? So 1250 minus 175.5. So what do I get? I get 1.0745 kg. Convert it to kg. Yes, so answer comes out to be 2.79 molality. This is how we solve molality. Yes, formulas on dilution often we use M1V1 is equal to M2V2, or we also come across M1V1 plus M2V2 is equal to M mix V mix. Yes, initial concentration, final concentrations we can use to solve these some questions. Please do remember all the formulae what I am taking so far. Yeah, so this is about expressing the strengths. Expressing the strengths. Yeah. Then percentage composition. One can check the purity of a given sample by analyzing this data. Let us understand, taking the example of water. Since water contains hydrogen and oxygen, the percentage composition of both the elements can be calculated. So mass percent, how do you calculate? So the water contains 2 atoms, hydrogen and oxygen. I want to calculate the mass percent of individual element. So mass percent of element hydrogen. Yes, mass of that element in the compound divided by molar mass into 100. So mass percent of hydrogen is equal to, how much mass of hydrogen is there? Yes, H2 means there is 2 divided by, what is the molar mass of water? It is 18 into 100. So 2 ones are 2 nines are 18, 100 by 9 comes out to be something 11.1. Yes, so this is the mass percent of hydrogen. Similarly, mass percent of oxygen. How many grams of oxygen? 16 divided by 80 into 100. Yes, that comes out to be 88.79. Yes, so this is how we calculate the percentage composition. You can calculate of any compound. You can take the example of say a C6H12O6. We know molecular mass of glucose is 180. So mass percent of carbon, 6 into 12 divided by 180 into 100. 6 atoms, 6 ones are 6, 6 twos are 12, 6 threes are 18. So 3 ones are 3, 3 twos are 6, 9, 3 fours are 12. So it is 40%. Then mass percent of hydrogen, 12 into 1 divided by 180 into 100. So 2 6 are 12, so 18. So 60 by 9, 9 6 are 54, 6 point something comes out to be. So it comes out to be 6.54, 6 remains, again 0, so 6.66% something. Then mass percent of oxygen. So 6 oxygen atoms into 16 divided by 180 into 100. So 6 ones are 6, 6 threes are 18. 160 divided by 3. So it is 3 ones are 3 5s are 15, 3 3s are 9, 1 remains, then 3 3s are 9, it continues. So it is 53.33%. So this is nothing but percentage composition of any compound can be found out. Empirical formula and molecular formula. So what do we mean by empirical formula? The formula of the compound which gives the simplest whole number ratio of atoms of various elements present in one molecule of the compound. Like for example, formula of hydrogen peroxide is H2O2. In order to express its empirical formula, we have to take out the common factor 2. So what will be the simplest whole number ratio? It is 1:1. So 2:2, right? It becomes 1:1. Therefore, empirical formula will be HO. Similarly, formula of glucose, C6H12O6. What is the, if you take the ratio 6:12:6, 6 ones are 6, 6 twos are 12, 6 ones are 6. So ratio comes out to be 1:2:1. And we can write CH2O. So that is the formula, that is empirical formula. Yes. And we know what is molecular formula. Yes. So here with this, we complete with the discussion of this topic, some basic concepts of chemistry. Some basic concepts of chemistry. So in the next one, we'll be proceeding with, please do remember all the formulae what I have discussed so far. In the next one, we'll be proceeding with the multiple choice questions on this topic, that is some basic concepts of chemistry. Thank you.